result that was very happy. We have Professor Bala with us. I request you to make the presentation.
Okay, I think I am giving the last presentation. Definitely this is not a very technical presentation like the previous presenters, and also it's not really my work. I'm just going to give you only an overview of climate change, mainly based on the previous IPCC report that was published in 2013. Right now, the new IPCC report is actually being prepared, and I'm actually also a lead author in that report. Strictly speaking, I'm not supposed to actually give any result from that new report that's being prepared. So I'm, probably in another couple of years, that material will be available. But I can assure you that there is nothing new. Science always takes long time to progress. So let's quickly, wind up this presentation. Okay, so as we actually today, I went to my room to a little bit work, and I saw this in Nature, the latest issue of Nature, and there was this editorial. And the main thing, what's the main message from that editorial? It says that, it was basically looking at, what happened in the last, this decade, and what should happen in the new, next decade. Major breakthroughs. And I think it listed basically that, detection of gravity waves, by the merger of two black holes, and also gene editing, that happened in biology as the major breakthroughs in the 2010s. And in 2020s, it basically says, you can see that the coming decade must focus on climate change. So that's what we are, basically from another 15 days, we are in a new decade, right? So why climate change is important? Let me, I don't want to also, of course, I've been working on climate change for the last 10 or 15 years. I can assure you that there is, two sides. One is, creating a scare, and another is denying climate change. But, I think what we should be aware of that is climate change is a long-term problem, and it is a slow problem. So it's going to come, maybe after we all die. It's going to be a major issue, maybe. Right? So with that in mind, but don't think it's going to come tomorrow and it's going to kill us, right? And even, let's say, big climate change in another 100 years, it's not going to kill us. We humans can, I'm sure, can adapt and also make, find ways to tackle climate change. I'm pretty confident about that. So, so I think I'm concluding. I'm putting the conclusions first. The first one is climate change is already underway, so we are going to show, basically evidences based on the past IPCC report. And there is a strong link between climate change, carbon dioxide, and our energy use. It all goes to basically our standard of life. Standard of life depends on energy usage. Energy usage leads to carbon dioxide emission, and carbon dioxide emission causes climate change. And climate change impact could be, as I said, severe and long-lasting, but that's basically, as I said, as a scientist, I have to be honest, so it's a slow process, it's going to take time. Climate change adaptation and mitigation would bring new opportunities, so one way to look at climate change is positively, that we need to actually decarbonize the energy system and look for alternate energy resources. And a good example was basically the previous talk, which focused on biomass. There is a huge literature actually on carbon dioxide removal, which basically one of them is actually basically using biomass for energy and then sequestering the carbon that is released by those power plants. So here is simple schematic. So basically, we all want good standard of life that requires energy, food, and water. It leads to this, and which basically means, so we are going to actually extract that energy from fossil fuel emissions and deforestation. Deforestation also actually is a source for carbon emission, and which leads to this climate change problem. And the big question mark is, what is the big impact on impacts on agriculture, water, forestry, health, etc., which could actually indirectly eventually affect our quality of life. I mean, that's the short story about climate change. And okay, so I just to quickly go through these slides. I'm sure some of you, must have seen these kind of slides in several places. So here is the, this is the major conclusion in the last IPCC assessment. That is, the warming of the climate system is unequivocal since 1950s, and many of the observed changes are unprecedented over millennia. So we're not millions of years, but at least on the order of thousands of years, like for example the last 20,000 years. So what we are seeing, this is unprecedented in the at least last, as I said, 20,000 years. Okay, so here is the iconic kind of map that shows the climate change since the pre-industrial time. I mean, it's red, but the numbers are small. Remember, you can see the scale here. It goes basically up to 2.5 degrees Celsius. So this is basically shows us that climate change. When you average over this at that time, the temperature change was 0.85 degrees on a global average. By 2013. Today it's actually about 1.1 or so. Because 7 or 8 years has passed. So the current global climate change is about 1 degree, right? All right. So, of course, this is surface temperature is a quantity that is continuously measured across the world. So basically, the headline making statement was that 2018 was basically the fourth warmest since the pre-industrial time, and in fact, the last. If you really look at 15, 16, 17, 18, they all basically record years in some sense. So in fact, the last 5 years, if you take the average, it is probably the warmest 5 years since pre-industrial time. As I said, this is all linked to carbon emissions and carbon dioxide concentration. So the instrumental record of carbon dioxide concentration was started sometime in actually exact year is 1958, the measurement started here. So since then, you can see the carbon dioxide is actually going up relentlessly. So this is actually a very good example. There is no, if you look at year after year, there is no year where the carbon dioxide concentration decreased compared to the previous year. Every year is more than the previous year. So because carbon dioxide is actually, this is a global mean CO2 concentration. So this really is some kind of integrated quantity. That's why you don't really see up and down in this. So relentlessly increasing. And in terms of numerical numbers, compared to this period, 1958, so approximately now we are about 60 years after that, the carbon dioxide concentration has increased by about 150 ppm. As a reference level, carbon dioxide concentration was 280 ppm in pre-industrial time, and now it is actually, last year it was 408. So we are well past the 400 ppm mark. So this is actually a longer perspective. So this graph actually is carbon dioxide in the last approximately 1 million years. So you can see the natural variability of carbon dioxide is confined to this level here, and today's level is somewhere here. So basically humans have made their footprint on the chemical composition of the atmosphere. And as you can see, I have made a statement here that it is really unprecedented in the last 1 or 2 million years, and possibly in the last 2 million years. So this level of carbon dioxide concentration was not seen on this planet in the last 20 million years. There are other consequences of increasing carbon dioxide in the concentration in the atmosphere. One is this, for example, this is the concentration of carbon dioxide in the seawater, surface seawater, which is also rising along with this atmospheric CO2 concentration, and the oceans are getting acidified. So you can see, the data doesn't extend long back. Only in the last 10 or 20 years we have data for ocean pH. So it is showing that the pH is declining, which means the ocean waters are getting acidified. And there are a lot of quantities that is relevant to climate change. One of them is what we call the ocean heat content. When we say the planet is warming, those graphs actually refer to the surface temperature, just what we measure at, let's say, 2 million over the ocean is the surface, which is actually very different from what is happening, let's say, in the deep ocean. We have to see whether the deep ocean is also gaining heat. So this basically tells you how the heat content of the ocean is basically changing across the. So this is the bottommost 700 meters. So everywhere you can see the heat content is actually going up. So as most of the physics people would know, there is a huge difference between temperature and heat content, right? So let's see how the ocean is. So basically, oceans have taken up about 93% of the heat that is trapped by greenhouse gases. And yeah, so this is how it looks, the zero orientation. This is the depth of the ocean, and these are the latitudes. So equator is here, this is northern hemisphere, this is southern hemisphere. I think what is interesting is, if you really look at this graph very carefully, the heat that is supplied to the climate system, it has gone only up to 1 kilometer depth at most in the ocean. So that means there is still a lot of time to go, because eventually when the system comes to equilibrium, the entire ocean has to heat up. So this is one reason I keep saying climate change is a long-term problem. It is a, at least when you look at the ocean, it is multiple 1,000-year problem, because this heat, you can see, since pre-industrial time, we have already passed more than 100 years, and the heat has penetrated only about 1 kilometer. If you look at the tropics, in fact, just the heat has penetrated only about 200 meters. So it's going to take a long time for climate change to be, really come to an equilibrium. So one consequence of this ocean warming is, any object when it is heated, it's going to expand. So most of the sea level rise, many people might be thinking that the sea level rise is caused by glacier melting or ice sheet melting. It is true, but so far most of the sea level rise is actually caused by the expansion of the ocean, because the oceans are getting heated up. Let's go back. Yeah, so basically sea level has increased by about 20 centimeters since the pre-industrial time. This is actually a basic science thing, what is actually causing climate change? Because we all know that there are many things in the climate system that can cause climate change. For example, let's say methane, carbon dioxide, N2O, land cover change, aerosols, etc. Even solar variability can cause climate change. So if you put all of them together and compare, what is the dominant forcing, which agent it provides. So you can see carbon dioxide is here. So carbon dioxide basically provides the biggest radiative forcing. We call this as radiative forcing. So somewhat, today, for example, the planet is net. This is the net forcing. So basically, about 2 watts per meter square is the heating rate of the, whatever changes that humans have done to this planet since the pre-industrial times. And there are various modeling techniques. I'm not even going to, this is just a summary talk, as I said. So you can see this is all, this comes from model quantification. So this is the observed temperature change about 0.8, as we discussed. And models are used actually to predict climate change caused by greenhouse gases here. And this is other forcing agents, mostly aerosols. And this is natural variability. Natural variability is basically, let's say, solar variability or volcanoes, etc. And this is internal variability of the climate system. So if you can see, most of the observed climate change is coming from these greenhouse gases, and which is partly mitigated by these aerosols. Okay. So some of the consequences, this is the impacts of climate change. I think where climate change is right now visible very strongly, it is actually in the Arctic. Arctic, basically, we have this, for example, ice is seen over Himalayas, right? We have ice sheets. So oceans also actually, there is in the Arctic, for example, we have what is called sea ice that floats, right? And most of the climate change, warming signal, it's actually stronger in the Arctic. So you can very clearly see here. The first bar shows the submarine measurements of ice thickness at various locations in the Arctic Ocean, and these are basically later periods. So ice thickness used to be about 3 to 4 meters here, and it got reduced to 2 meters or something. So basically, there is a large reduction. In fact, when people look at ice area, it has shrunk actually in September, which is the time when ice is minimum in the Arctic. It has already shrunk by 50%. And if you look at the volume, ice actually has shrunk by 75%. So if you really want a very compelling evidence for climate change, Arctic sea ice is the place, right? And these are basically again melt rates computed for the, this is Antarctica and this is Greenland. So these are all, basically rate of change of what I would call ice thickness or something. So you can see there is a lot of, this red basically means the melting of ice. So Greenland is melting fast, but if you look at Antarctic, it is kind of still quite stable. Most of the, if you really look at here, Antarctic ice sheet is actually growing. So this is the contribution to sea level rise by the various sources. So right now, glaciers are contributing the most, followed by Greenland. Okay. Okay, CO2 emissions are the main drivers. I just want to kind of provide a broader view on this. One is the global energy consumption has actually tripled in 50 years. So if you look at actually how much energy we are using in our human system, this is basically the most of the energy consumption actually right now coming from oil, gas, coal, and still sadly only 50% or 15% of the energy still comes from renewable sources, and 85% of the energy actually comes from fossil fuel. And this is, already I showed you this graph that shows the carbon dioxide concentration increase. Then, okay, this is just a simple, convert 1 ppm of increase in carbon into how many billions of tons. So 1 ppm actually on a global level, it's actually equivalent to 2 billion tons of carbon, right? So, that's 1 ppm. 1 ppm, we know that 1 molecule of CO2 is 1 million molecules. And so basically, approximately the carbon content of our atmosphere has increased by 250 billion tons since the pre-industrial time. So this is basically, I already showed this. This is the CO2 concentration in the last 800,000 years. This comes from basically the air bubbles, air bubbles that are trapped in Antarctica. People go and drill the core and get the ice core samples, and you analyze the air bubble that is trapped in those ice sheets. So basically, you get these numbers from that. So you can see CO2 concentration basically has fluctuated between 280 ppm to 180 ppm. Today, somewhere we are here. This is basically the last 2,000 years. So CO2 was pretty stable until the industrialization began. The last 100 years or 150 years, CO2 is going up very rapidly. And then this is there is a program called Global Carbon Program. They basically do a carbon budget, which means basically they track how much carbon we are actually each year putting into the atmosphere, and how much of that actually goes into the ocean, and how much of that is actually taken up by plants on land. And then the remaining, basically, it's a very simple budget. If you put carbon dioxide into the atmosphere, it has only 3 places to go. One is into the land, and second into the ocean, and whatever is not taken up by these two, the remaining is going to stay in the atmosphere. That's how the system works. So, according to this, this is a global network of scientists who basically crunch these numbers each year. And so there is actually, this is very interesting. Every year a paper is published by this group of scientists. So it's basically Global Carbon Budget, 2019, this one. So anyway, let's look at what this figure shows is since 1990, these are the carbon emission rate, how humans are emitting carbon dioxide into the atmosphere. So right now we are emitting 36.8 gigaton, that is billion tons of carbon dioxide into this planet. So in 1990 it was 22. So compared to, I think somewhere I wrote, but anyway, I think even compared to this period, we are actually emitting close to 70% more carbon dioxide than just about 30 years back. Yeah, so that's 61% over the 1990. That's a rate of emission. Remember, that's a rate at which we are doing. And then these are the country level, this particular program also calculates the country level emissions. So this is the, right now China leads the world, right? And next is United States. And third is actually India as a country. India is number 3. And this is 28 countries, European Union. So, and this is all rest of the world, alright? So, the short story is that as a country, India is number 3 in carbon dioxide emission, and after China and US today. So let's quickly go through this future climate change that is, as predicted by climate models, right? So right now there are, many countries have their own climate model, and India also for the first time, it's actually providing input to this new assessment on climate change. The model is actually developed at the Indian Institute of Tropical Meteorology in Pune. The number of models that actually provide input into this assessment has been actually increasing very rapidly, almost exponentially. For this assessment, something like nearly 100 models are providing input to this. So, for the previous assessment that was made in 2013, something like 60 models provided input into this assessment. So, all the assessments are statistical assessment now. It's not based on a single climate model, so you can actually get a range. So, you will see in many of the graphs, multiple lines or a shading, which basically shows the statistical assessment. Okay, so first carbon dioxide projection. So this basically, this projection of, let's say, carbon dioxide emissions. So here is the carbon dioxide emission rate. So somewhere we are here today. So this is not in terms of carbon dioxide, this is in terms of carbon. So basically billion tons of carbon. So we are somewhere around 10 billion tons of carbon dioxide per year we are emitting. So if we go on a business as usual pathway, emissions could actually double from today, more than double actually, 25. Today we are about 10, so 25. And then these are various what I would call as socio-economic scenarios. So these are all, nobody of course knows the future, but this is basically economists think. This is how, if something like this happens, this is how carbon, so they'll use the fossil fuels or deforestation, etc., and you get these emissions, right? So there is one optimistic, very optimistic scenario is this, where emissions actually peak before 2050, and it actually comes down after that. And in fact, it becomes zero somewhere around 2070. That's the scenario, in fact, what we call as 2-degree scenario. I'm sure some of you may have heard about that. In the Paris, one of the pillar stone, really of Paris Agreement is that we should limit global warming by 2 degrees by 2100. Right now we are already 1 degree, so maximum, this century, another 80 years, let us not exceed another 1 degree warming, because again, based on various fields of research, it has been assessed that if you cross 2 degrees, maybe it is dangerous. Again, it's a very subjective thing. Dangerous is not a scientific term, it is really subjective term, okay? Alright, so if you follow the business as usual, carbon dioxide level could reach as high as about 1000 ppm. So there are 2 extreme scenarios. One is this 1000 ppm, and another is somewhere close to where we are today. Basically you can see in this low emission scenario, carbon dioxide actually goes up a little bit, maybe up to 450 ppm, and then it comes, basically after that it comes down. So, so what's going to happen if we follow any of this scenario? So, let's, these are all, of course, as I said, nobody knows the future. This is all, but we have very good confidence in models, remember. And also, all these assessments are statistical assessments. So you can see shadings. For example, there is a huge range for this RCP 8.5. So the mean projection for RCP 8.5 is compared to the pre-industrial standards, something like 8 degrees warming global. So that's really, that is a scary scenario, I would say. Definitely 8-degree warming. I think the world is not going to be like what we have today. I think already, many places you can see year after year in India, during the heat wave times, temperatures were crossing, 40, 45. And right now, in fact, if you turn on to the news, you see that right now it is in the southern hemisphere summer, and Australia is really burning actually. The temperatures, they are seeing unprecedented temperatures. This is only for 1 degree global mean warming. We are already seeing big changes at the regional level. And so this is the RCP 2.6 scenario, that's the low emission scenario. You can see here the warming is, you take this difference between this level and this temperature, so that's about 2 degrees. So only if you follow the low emission scenario, where carbon emissions actually become zero by 2070, there is a hope of actually limiting warming to 2 degrees. And so these, we do have these climate models now. They can actually project what are the changes. They are really three-dimensional model. Three-dimensional in the sense, top of the atmosphere to all the way to the bottom of the ocean. So you can get multiple quantities from these. So this is, for example, for the high emission scenario, RCP 8.5, from 39 models, this is the projection for precipitation change, rainfall change. So I think one thing that's very clear is, there's a lot of changes are both positive and negative. There are places like here, precipitation increases, and then there are a lot of these places here, particularly in this Mediterranean area, precipitation decreases, and then precipitation increases in the high latitudes. There is a solid science explaining this, why the pattern has to be like this. And this is soil moisture. Soil moisture, I think, is a really soil moisture is a better quantity than precipitation, because precipitation tells only the input to the land. So if you look at the budget, there is also evaporation runoff. So when you calculate all of that, the end result is, either you have to look at P minus E, or you can look at the soil moisture. So soil moisture, actually, you can see in many places, the soil actually dries. India is not bad, but look at this Mediterranean area. These are all actually desert areas in some sense. This is a sedimentary area. Brazil is having a serious problem. South Africa. Many places, actually, the models actually predict overall water budget will be actually negative, because evaporation actually, you are heating the land so much, so you lose a lot of water. Even though the precipitation increases, the evaporation actually increases faster than precipitation, so you get this negative budget. And sea level projection. So my rule of thumb is, of course, people debate a lot about this sea level rise, whether it's going to be 60 centimeters in this century or 1 meter in this century. But let's not worry about that. I think there is definitely sea level is going to rise, and it is extremely slow. This is something, it's even slower than temperature change, and in fact, sea level will keep rising for thousands of years, based on what we are actually doing here, because it's extremely, we all know that inertia in the system. So the ocean has, really big inertia, and so it's going to, and also most of the sea level in the future will come from melting Greenland and melting Antarctica, and that's a, tens of thousands of years process, so it will be very slow. But anyway, what is really needed for us in the short term is what's going to happen in the next, this century. So definitely, even in the low emission scenario, we look at here, the projection is about 60 centimeters, and high emission scenario will be about a meter. And then, this is a work based on our work here. So this is a projection for India. So you can see India, basically the high emission scenario, the mean could be about 60 degrees warming, and this is the low emission scenario, about 2 degree warming here. Again, I wanted to focus on this shading as well as the solid line. Solid line is the ensemble mean, we call that, averaging of multiple models, and the shading basically represents the range of results that you get from models. and then this is the precipitation projection. So precipitation, you can see, really very difficult variable. Negative, positive, negative. So some models are actually predicting positive changes, some models are predicting negative changes. So the mean in take is a slight increase in rainfall in all the scenarios for India. And then there is a very important result which is actually consistent across the model. That is, the number of rainy days will decrease. You can see this red actually shows a decline in number of rainy days. But at the same time, if you calculate what is the maximum intensity of rainfall or average intensity of rainfall, that increases. So what this tells you is that when it rains, it is heavy, and you actually have more dry days. I think that's what one of the consequences of climate change. And yeah, so do we have evidence for this increase in intensity of the rainfall? So here is actually work that is actually done at COS from another research group. So this shows, this is the, just roughly the number of extreme events in the period of May and June, starting from 1950 to 2015. So you can see, it doesn't matter which month you look at, the number of extreme events are actually already increasing in the last 50 years, the 50 years data shows that. And one of the questions, this is again an academic question, when will we know statistically that the climate has changed? What do you mean by that? There is a variability in the climate system. So if we call climate change as a signal, so the signal has to be bigger than the variability in the system. So you can actually assess, based on the models, you can assess the noise or the variability at each grid point, and then also you can look at the signal at each period and then see when the signal is bigger than the noise. So this is a very simple metric, that is S by N, signal to noise greater than 1. So basically you can actually calculate the variability, standard deviation as the variability. So, so basically, is the climate change bigger than 1 standard deviation? Or this one shows 2 standard deviation. So you can obviously see many places climate change emerges early if you use signal to noise ratio greater than 1. But in many places it arrives, it can be seen later. For example, this blue tells you, you can confidently say climate change has arrived only in 2060. But most of the tropical area like where we live, I think it doesn't matter whether you use 1 or 2, climate change has already arrived, right? And yeah, this is a very similar plot. So, but this is based on 37 models. Most of the tropical area climate actually signal arrives by 2010 itself. So we have, the tropical area climate change has already arrived. And okay, I think it's maybe, how much time do we have? Maybe 5 minutes. Another 5 minutes, okay. So, I talked about this global carbon budget. So this is the carbon budget for the latest year, 2018. So basically this is an average over 10 years. So this tells you where carbon dioxide emissions are coming from. 86% of our emissions are right now coming from fossil fuel emissions, and 14% is coming from land use change or deforestation. And it's interesting, out of that nearly a quarter gets into the ocean and a quarter gets into the land. And only 50% roughly, so you can see the numbers here. 44% remains in the atmosphere, nearly 30% goes into the land, and 23% goes into the ocean. That's a kind of a conclusion, but of course this comes from ground level work all the way scaling up to the global scale. And yeah, this is basically where the fossil fuel emissions are right now. In fact, interestingly, coal, mainly driven by China. Coal is the dominant fossil fuel, and then oil, gas, and cement production. And yeah, this is again an academic question. When will, suppose, I'm sure obviously we are going to emit for next 100 years or 200 years. After that, sure, we are going to run out of fossil fuel because the resources are limited. So academically, so when will carbon dioxide return to the pre-industrial level? So apparently, it's not going to return for another million years. It doesn't matter even if you stop emitting fossil fuel. Of course, I'm talking really academic question here, right? So what are the physical processes involved in removing carbon dioxide? So it seems, this is basically, this graph shows how much percentage of the carbon dioxide remains in the atmosphere, whatever we emit, in a, this is time. So after 100 years, you can see about 40%, which is basically the number that we see today. If you emit something, nearly 40 to 50% of the carbon dioxide remains in the atmosphere. With time, this is 1,000 years, still nearly 20% of the carbon actually remains in the atmosphere. Even after 1,000 years, that means carbon dioxide levels will be higher than pre-industrial time because of human emissions. And even if you do 10,000 years, carbon dioxide actually doesn't come back to this level. Still something like 10% remains in the atmosphere. So, that's one reason why I said this is a really, really long-lasting problem. It's not going to go away very easily unless artificially we do something. So these are the chemical reactions, of course, involved in those various time periods. So in the short period, like 100-year period, basically plants are the ones that are basically doing it, right? And then on a time scale of 10 years to 1,000 years, oceans are reinvolved in taking up carbon. And then reaction with calcium carbonate, this is called weathering our rocks, and then these two processes are basically. Eventually, there is this geological process, which basically where rocks are involved in reacting with carbon dioxide, along with the precipitation is the process that will remove carbon dioxide. So you can see the processes actually go all the way to 1 million years. So what we do today, the footprint of that human action will be there. If you don't do anything, it's going to be there for 1 million years or so. Okay, so now we are coming to the end. So I just to quickly summarize what are the kind of impacts of climate change that matter. More intensive days, frequent floods and droughts. That I showed you the evidence that number of rainy days will get reduced, but more rain, the intensity will go up. And then intense hurricanes. There is the evidence for this. The hurricanes actually get number decreases, but the intensity increases. Sea level rise, roughly as I said, 1 meter per century, and then glaciers melt away. Particularly, this could be a serious problem for the Himalayan glaciers and downstream people. Loss of plants and animal species. This is a very hot topic. In fact, already, maybe not because of climate change, but because of other human actions, already there is very strong evidence biodiversity is a serious, that's the extinction of species. That's a serious problem already. And then infectious disease spread and human health. Ocean acidification. This is a problem that is, I have not covered here, but I did actually show one slide where the pH of the seawater was actually decreasing. So ocean is, basically at least even if the marine life is not extinct, it could lead to different species composition. And another serious problem, this is again not confirmed, is climate refugees. In fact, there is a lot of, for example, you see in the Mediterranean area, basically adjoining North Africa, it's going to get more dry. So, in fact, Western countries are worried about this, that more people will migrate from North Africa into Europe, UK, and that's one of the main worries, that more people will be coming into developed countries. Maybe we are already seeing discussions of this. I don't know whether that's partly climate maybe actually can be attributed to that. All right. So people, of course, you may have seen some schematic, scary diagrams like this. So this is the impacts of climate change for a 4-degree warming, produced to one of the climate warming centers, and basically reduced crop yield, stronger tropical cyclone, forest fire could increased drought. Yeah, this is the area where a lot of drought is expected. Melting ice, more heat waves, rainforest loss, ocean acidification. So that's kind of a simple schematic on impacts of climate change. And then, always, I used to have a question on this, that is, when will really human life will be threatened by climate change? So, actually, interestingly, there are a few papers on this. There is a quantity, we all know temperature, right? There is also another quantity called wet bulb temperature, which basically incorporates the effect of water vapor into this. So, when the wet bulb temperature is, for example, above 37 degree, that's exactly 37 degree, then people would die. If you are exposed to a condition of wet bulb temperature above 37 degrees, within an hour to 4 hours, I think people die. And right now, where do we have that kind of conditions? Literally very few places. I mean, I don't think you can see this graph. 37 should be somewhere in that color, you don't see that. So most places on the planet is actually habitable. So because the wet bulb temperature never exceeds that. I mean, the dry heat could be, temperature could be 50 degrees, no problem. 55 degrees. But in a very 100% humidity, is there, then 37 is the maximum that you can actually tolerate. But if the planet actually becomes something like 11 to 12 degree global mean warming, then you can see many places in the tropical and subtropical area, it does actually reach that 37 degree. So fortunately, we are not going to reach that level. So, the maximum prediction I showed you was about even for high emission scenario about 8 degrees or something like that, right? Okay, the conventional solution, I'm sure you must have heard about adaptation and mitigation, so I'm just, this is a schematic. For example, let's say, we can all live through if we all, provide, let's say, air conditioning in every building, and, that's a kind of adaptation measure. For example, sea level rise, how would you, you're not going to stop sea levels from rising, but you could actually always build walls, along the beaches to, that's a kind of, an example for adaptation. So that, right now the current thinking is, well, anyway, there is some amount of warming that we have already committed, that's not going to go away. So we have to do some kind of adaptation. And then also what is called mitigation. So basically it involves modifying our decisions, activities, and way of thinking to adjust to a changing climate. So basically you adjust to the changing climate. Of course you can adjust to some extent, not if the climate change is too big. So that's adaptation. And the next is mitigation. So mitigation basically involves activities where carbon emission is basically reduced on a per year basis in the future. So what are those activities? I think the best example is basically renewable energy, right? So yeah, solutions. There are various ways. Conservation. Oops. Oh, yeah. Solutions to global warming. So conservation, these are of course well known. I don't have to get into that here. Investment in green energy, and then one can work on energy efficiency, carbon efficiency. Most people don't talk about population control. I think, in my opinion, that's one of the serious problems that I think politically, it's not the right thing to talk about. But remember, in fact, there is an equation, not an equation, it's an identity that's called Kaya identity for carbon emission. The first term is basically carbon emission is equal to population times GDP times energy efficiency, carbon intensity, energy intensity, carbon intensity. That's all. So the first term is really population, because every human being, of course, we need food, water, and energy. So obviously the population is a major driving factor for carbon emission. And I think there is also recently some, I have put this last thing here, that is geoengineering. It basically involves artificially modifying the climate system. So this is a solution that has been proposed in the last 15 years or so. And there are, in fact, serious research, including models, people are actually looking at it. One way is basically, can we put some sulfate aerosols in the stratosphere, where, because the aerosols are good scatterers. So, in fact, in theory, everything is worked out by models, and we do have a lot of simulations now. So the idea is inject aerosols in the stratosphere, where these aerosols would reflect sunlight and basically cool the planet. I mean, that's an idea which is scientifically fine, but I think, there are a lot of questions around that. One of them is it moral to do that? Is it ethical to do that? Is it lawful to do all those kind of things? So there is, but because of those issues, this has not been so far. This particular solution has not been discussed at any United Nations meetings, but other meetings these are being discussed right now. Okay, so also, this is a couple of things to think about. The first statement is by James Lovelock. So he basically came out with this idea of Gaia, planet as a single living organism which manipulates its climate to benefit itself. That's the kind of idea proposed. So he basically said some years back, the Earth can actually support only 1 billion people. And he actually said 6 billion people living on this planet could actually quickly run out of resources and we can get into a serious problem. But he has been proven wrong, I believe, because we are already 7.5 billion people on the planet. And this is also again found this philosophical statement. There is a sufficiency in the world for man's need, but not for man's greed. So those are really how we view our environment and human society. Yeah, that's all.